Hello, and thanks for joining us today for the latest Technology Networks webinar, Do It With Our Uncle, We Mean Protein Characterization, sponsored by Unchained Labs. I'm Anna, editor at Technology Networks, and I'm here to introduce the event. I'm pleased to have Joe Barco and Dina Finnan joining us today. Joe Barco is the Director of Product Marketing at Unchained Labs. He is responsible for new product launches and product development for protein analytical tools. Joe received his PhD in chemistry from Stanford University. He has spent 15 years in the biotechnology instrumentation arena, first as an applications scientist, followed by positions of increasing responsibility in product management and marketing. His main interest is bringing better tools to scientific discovery. Dina Finnan is an applications scientist at Unchained Labs. She is responsible for developing proof-of-concept studies to support our protein analytics customers and new product development. Dina received a degree in biology from MIT and a PhD in biochemistry from Stanford University. Prior to joining Unchained Labs, she spent 5 years engineering stable proteins for industrial biotechnology applications and led a group responsible for developing model systems and predictive assays. A warm welcome to you, Joe and Dina. Following the webinar, we will have a Q&A session, and we would welcome any questions that you may have. To ask a question, you should enter your question into the box on the left-hand side and click Submit. We will answer as many as possible during the time available. Any questions we don't have time to get to, we will be sure you are contacted offline with an answer. If you experience any technical issues, please use the question box to request support. I'll now hand over to Joe.
Thank you, and thank you everyone for joining us today. Our seminar is titled Do It With Our Uncle, and just to be clear, I don't know what type of webinar you are planning to hear today, but we're actually talking about instruments and protein characterization. So what we're here to talk about is what our uncle does, and what it does is it combines 3 different detection methods to give access to key parameters around protein stability and aggregation. Many of these things are probably things you have already heard of or use if you do protein characterization or formulation development or screening. A few you probably don't do because current tools don't do them well, or the instrumentation is not available, or both. This is a list of 10 applications that can be done on the platform and immediately analyzed. And by that I mean samples are loaded in, the experiment is run, and data is automatically analyzed when the experiment is over. We know people like to come up with off-the-wall, cutting-edge things to do, and Uncle helps them to do that with freeform mode, where you can combine the detection methods in non-standard combinations that may be more interesting to you or your particular experiment. This concept of combining technologies happens all the time. In fact, you probably have an example sitting with you either in your hand right now or in your pocket, which is a smartphone. So just 10 years ago, if I was taking a road trip, I would need all 4 of the individual items on the left. I would need a GPS to tell me how to get to my destination, music to play along the ride, a camera for when I reach my destination, and a phone to keep in contact the whole way. So right now it's crazy and old-fashioned to have all of these separate devices, but not only that, it's inefficient because I have 4 different companies to work with, 4 different sets of plugs, extra space, extra requirements of things I need to carry, and all of the inconvenience of the concept of having separate devices. It's just more efficient to have them all combined in one device. On the protein characterization side, there's similar things that are creating a need to combine detection methodologies and gain efficiencies from having a simple instrument. One of that is because there's changes upstream and downstream of current characterization processes. So upstream, antibody engineering has become more efficient and more accurate. And so as a result, more candidates are coming into characterization that are good ligand binders and are good potential drugs. This requires more compounds to undergo stability testing. At the downstream end, manufacturing processes have become more efficient and produce drugs at higher concentrations, and dosing has become higher with the advent of more high-dosage injectables. So these factors increase the risk of aggregation and viscosity affecting drug development. So characterizing these things earlier on is more of a need and more of a requirement than it had been just in the very recent past. So as I mentioned, what UNCLE does is it combines three detection methods. It combines full spectrum fluorescence, so a full spectrum of fluorescence activity in the well, static light scattering methods, and dynamic light scattering methods. So what these do is it gives access to some of the applications we'll talk about today. To gain efficiencies of using this, we have to cut down, and we have cut down on the amount of sample required, so it's 9 microliters per sample well. To do a lot of stability measurements, you need thermal degradation methodology, so we have a temperature control between 15 and 95 C, so you can ramp up or down depending on your protein and your protocol requirements. And most of our measurements are label-free, which is that I do not need to have any extrinsic dyes present to do any measurements. So if I look at this in comparison with kind of the gold standard methodologies for doing measurements already on the market, if I look at this, I simply have, it breaks down to 200-fold less protein I need to do these measurements in comparison to if I had the three separate instruments doing this. So previously, the gold standard of TM measurements is DSC, which requires a large amount of protein and reads one sample at a time. Measurements for thermal aggregation have been done in many ways. One way is simply by looking at light scattering methodologies. This requires a separate instrument and a higher protein concentration. Dynamic light scattering, the most efficient way to do it has been on a plate read format, which still requires a fair amount of sample to maintain a sensitive level of detection. So if I combine all of these detection methods in one platform, you can see immediately I've cut down my bench space by about a factor of 3 in addition to the amount of protein. Plus I have one software set to analyze and to work with. I have one vendor to work with. I have one set of software updates and instrumentation to work with. It's just simply more efficient to train people on one instrument versus 3. So the key to having the low sample volume and to maintain performance is the uni. And the uni is, you can see here there's a blue holder and a black piece. If I zoom in on the black piece, I can see I have small microcapillaries present. There is 16 microcapillaries present per uni frame. These frames are designed so that I can access it with a multi-channel pipetter. This is a 16-channel multi-pipetter accessing the entire uni at once. In concept, in practice, most people will use an 8-channel pipetter and access alternate wells to fill it. So it comes with this filling station. You line up your samples, inject your sample into the uni, put seals in the blue uni holder, and then add the uni to that. It clamps closed. The intent is that the sample is sealed so that you can run it without risk of cross-contamination. The addition of the sample in this manner ensures that we do not have sample leaking on the outside of the capillaries, and that we can actually run that without worrying about contaminating the instrument or adjacent samples. So 16 wells per uni. I can run up to 3 unis at a time. The cuvettes are a quartz, so that they are higher quality for light transmission and retain and reduce protein sticking to the surface of the glass. The samples are uniformly heated and there's no cross-contamination because of the sealing. The sealing method ensures that we can actually run for much longer than 1 or 2 hours, which is a typical TM-TAG experiment. So you can access many different things that you might not be able to do if the instrument just did thermal melting. So some of the examples of things that it can do are shown here. We're not going to go into detail on all of these today. These can be accessed through application notes on our website or by following up with us after the presentation. I will say that not all of these use all of the different application methods, but we will talk about ways that some of these detection methodologies can be used today. Finally, what we did was we made sure that the fact that you have 48 samples coming at a time and all of this data coming to you, the benefit of that is lost if we don't have good, easy data analysis. So we strive to make data analysis for UNCLE straightforward and easy, which is that in fact most of it is done without the user having to intervene. So the user enters sample information, they put the unis in the instrument, they click start, and then leave for an hour or two, come back, depending on the experiment, come back, and they see their data is already analyzed and sorted. So because the instrument's new, we thought we'd talk a little bit more about how kind of that process is of setting up the instrument and use some case study examples as data. So I'm going to turn it over to Dina to continue with the presentation.
Thanks, Joe. So if you are characterizing biologics or you worry about protein stability, then UNCLE can really help you with steps all along the pipeline of your process. And so I wanted to talk first about our sort of workhorse application, which is the TM-TAG with optional DLS. So I wanted to walk through that. And the case study, we're going to use 12 different monoclonal antibodies for this first one. And I run them all in triplicate at 0.5 mg per mil, and they're all just in PBS. So from one experiment, we want to get these 3 pieces of information out, and I'll demonstrate how we can use those different pieces of information, so the melting temperature, the temperature of aggregation onset, and the sizing and polydispersity, how we can use all of these to make decisions in our process. So as Joe mentioned, the software has a very friendly user interface that guides you through what to do. So I'm going to start on the right of these buttons on the main screen and go backwards. So the snapshot button just allows you to trigger the lasers, and you can capture single spectra or DLS measurements if you don't want to do a whole experiment and you just want to get an idea what your samples look like. The load method button just allows you to load a method you've already created and saved previously. And then, as Joe mentioned, the freeform mode is really cool because it allows you to design your own type of experiment using any combination of the 3 detection modes. And you can do sort of any combination of thermal ramps up or down, or incubations and holds. So that sort of gives you the flexibility to create your custom experiment. But on the left are our standard applications, and that's what we're going to work through today. So that's the button that I would push. That's where all of our list of standard applications are found. So here's the list of applications displayed, and the TM-TAG DLS is listed first. So just selecting one of those radio buttons, the software is then going to guide me and prompt me to set up that experiment. Okay, so now I can enter all of my samples into my unis, and you can see this visual display of what the unis look like. So any wells where I've dragged samples in turn green, and the samples that I've left empty, or the wells I've left empty, are gray. And so I can put in as much detail as I want about my samples, the buffers, the attributes like pH, and I can enter all that in and just drag and drop into the unis to sort of see visually where I've put my samples. And then it's going to direct me to set up my ramp here. So I need to do 3 things. I need to decide 3 things to start. A starting temperature, and I'm picking 15 degrees. That's the lowest that the instrument can go. And then a final temperature, and I'm going all the way up to 95 degrees Celsius. The other thing I need to decide is the ramp rate. So obviously if you ramp faster, your experiment will be done earlier, but there's this risk that if you heat up a protein too fast, the melting temperature that it reports won't be accurate because you're sort of unfolding your protein too quickly. So that's why I'm choosing to ramp up relatively slowly here. I picked 0.3 degrees per minute. And that's pretty typical. I think our experiments usually go somewhere between 0.3 to 1 degrees per minute. And so that sort of gives you an idea. So then it depicts the ramp in the picture there. Now, if you see those 2 check boxes on the top, that allows me to choose the option for collecting initial DLS and final DLS on the same samples at the same time. So just by clicking those 2 check boxes, it's now giving me options for how long to collect that data. And the default settings are usually good. So that's for 20 seconds per well, I can get this additional data on the same sample. So if I choose to collect both the initial and final, I just check those boxes. I load my 9 microliters into each well of my uni, and then I just hit start and walk away from UNCLE for a couple of hours. When I come back to the machine, my data has been collected and it's already analyzed for me. So here's a screenshot of all of my antibodies, and they're all overlaid with their unfolding curves on top of each other here. So just remember that I'm looking at the intrinsic fluorescence of the proteins, and this is coming mainly from the tryptophans in the native sequence. So we're not using any extrinsic dyes, and we're just monitoring the unfolding of the proteins. And you can see the range of the melting temperatures for this group is going from about 63 degrees to about 73 degrees for the TMs. And you can see just by looking that the curves sort of have a variety of shapes because different proteins tend to unfold in slightly different ways. If I look at a screenshot from the whole analysis window, you can see on the top left there's a heat map with red, yellow, and green colors. So this is giving me a visual representation of what is happening to each of my samples. So there's a drop-down menu right below, and I can choose which parameter to color the heat map with. So I've just picked TM here. And so you can see that it's kind of putting them into one of three buckets. So the red would be the lowest, the yellow would be medium, and green would be high. So that just helps me to quickly look at my samples and see what trends I'm getting and what, if I'm looking for particular patterns or something like that. And those colors will carry through to my tables below, so I can also just see which ones were the best, which ones were the worst. And then you can see the little check boxes to the right of the heat map. I'll talk more about that in a minute. And then finally, I have these 4 ways of displaying my fluorescence data and analyzing it. And I can just toggle between them to view my data in different ways. So I'm going to look at that next. Okay, so for the fluorescence data, a pretty common way to analyze that is using the ratio of fluorescence at 350 to 330 nanometers. So that usually looks pretty good for most proteins, but we also like this method called the barycentric mean, or BCM. And that actually looks even better for most proteins. So what that is the wavelength that divides the area under the curve into 2 equal halves. So it's a ratio of sorts, but it also captures the changes in peak intensity and the peak position. So some proteins undergo redshifts as they unfold, and that can capture more than just the ratio of 2 set wavelengths. So in this example, which is pretty typical of an antibody, you can see that both analysis methods give you very similar TM values. Those are essentially the same. But the BCM data, when you look at the curve, it's just a little bit smoother and less noisy. And the ratio, it doesn't take into account all of the data we're collecting. Like I said, it's just sticking to those 2 set wavelengths. So if your protein tends to do anything unusual as it unfolds, this gives you the flexibility to quickly switch analysis methods and just look and see which one gives you the best sort of analysis. The other 2 we offer are you can look at the area under the curve or the peak height, and you can just, again, just toggle back and forth and see which ones you want to choose. Okay, since we collect the full spectrum of fluorescence, you can double-click on any sample, and you can go into this window where you see the full spectrum. And you can look at it in a couple of different ways here. So you can animate the whole ramp, which would kind of spice up your presentation with a movie of what's happening across the ramp. Or you can pick specific points that you want to display. So you can see as the protein unfolds, the main curve might be coming down, and then you might get spikes where the aggregation is happening. So this allows you to look at things other than intrinsic fluorescence if you like, because we are collecting that full spectrum. And then finally, you can go a bit further into your data. So if you or your audience that you're speaking to, if they're accustomed to looking at DSC data for TMs, then you can right-click and show the differential curve for your data. So that kind of, people sometimes like to see how it's picking the TM. And so you can just select to show that if you want. And you can also click these check boxes and put drop lines down to show where it's calculating the TMs or the T-ags. And then finally, you can export any of this data in table form or Excel form, and you can export the graphs as images as well. And then I should also mention, you can check multiple boxes at once, so you can see things overlaid on top of each other, which is nice for comparison. Okay, so let's go back to our set of 12 antibodies that I talked about for screening. So it was easy for me to throw out the red ones in the heat map. Those were the worst, so they were the least stable, and they had the lowest melting temperature. But then there was this pair of constructs, antibody 2 and antibody 10, and they had similar melting temperatures, and you can see they're both yellow if you look at the table below. And they had very similar melting temperatures. They weren't the highest in my group, but they're not too bad. And I wanted to look at them in a bit more detail, I think because the data from other types of assays made them interesting to me. So their melting temperatures are so close. You can see 67 and 68 degrees. They're essentially the same. So what does that mean? What can I really do with that information? And I'm also just showing the triplicate measurements for both. So the 3 antibody 2 samples were in greens, different shades of green, and the antibody 10s were in different shades of purple. And you can just see how reproducible the data tends to be from this type of experiment. They're right on top of each other with very, very small CVs. So what do I do when I have these really close melting temperatures? How do I go ahead and make decisions? So we can see aggregation at the same time. And here I'm pulling out one replicate of antibody 10, just so that the slide doesn't get too busy. But you can see the same fluorescence curve on top. That's the unfolding of the protein. And on the bottom graph, I'm looking at aggregation by static light scattering. And so you can see that the software is calculating the temperature of onset of aggregation to be 69.7 degrees. And so that's very close to the TM. That kind of implies that the unfolding of this protein is linked pretty closely to its aggregation. And the onset temperature is defined as the point in that curve where it reaches 10% of the peak. So it's really when it starts to rise. So that's how you get the T-ag. So I can choose to look at those on the same graph, or I can separate them so it doesn't get too busy. And we use 2 different wavelengths to track aggregation at the same time. You can see them both, again, at the same time or separately. So here I'm showing the 266 nanometers, and that's really good for high sensitivity for smaller particles that tend to come up earlier. And that's what I'm showing here. And you can see, again, I'm showing the unfolding curves and the SLS 266 for both of the antibodies. Antibody 2 is always going to be in green, and antibody 10 is always in purple. At 473 nanometers, which is the other wavelength we collect, you have a bit lower sensitivity but a much higher dynamic range. So here you can measure higher amounts of aggregation before the signal will saturate. And so here you can see they tend to come up a little bit later because we're looking at larger particles, a little bit less sensitivity, but you can sort of have a bigger range of seeing things. And so here this is kind of interesting because you can see that the antibody 2 never really shows any onset of aggregation. It's essentially flat, that green flat line at the bottom, whereas the purple aggregation curve goes up at around 73 degrees. So let's look at the onset of aggregation for these 2 antibodies just in a table. So in the graph, I'm showing just the 266 nanometer SLS, but in the table, I'm showing the T-ags for both wavelengths for comparison. So if we just look at the numbers, it looks like antibody 10 has a later onset of aggregation, 69 versus 62. But when I look at the curves by eye, it really seems like antibody 2 barely shows, that many counts. The counts are on the y-axis. So it looks like intuitively antibody 10 is actually aggregating more, but the onset shows that it's later. So if I want to, I can go look at the raw data, which has those counts on the y-axis, and I can see sort of how much aggregation I'm getting. So here are the counts in the table, so same graphs, but for both the 266 and the 473. So I can see that for antibody 2, I'm getting an order of magnitude less counts at the end of the thermal ramp than for antibody 10. So that's really just what we saw by eye. And then I'm not getting any onset of aggregation for antibody 2 at the higher wavelength. So it's not forming any large particles even at 95 degrees. So I could stop right here, and I could just conclude sort of qualitatively that the 2 antibodies have very similar melting temperatures, but maybe antibody 2 is a bit less prone to forming large aggregates in PBS, and maybe that means that it's going to be more stable over my storage processes or manufacturing. But I don't want to rely on just this one measurement, since I have the capability to collect other types of data with the same instrument. So if I want more resolution with what's happening in the same exact experiment, I can just choose to look at that DLS data that I collected when I checked those 2 boxes earlier. Okay, so here's a screenshot of what the DLS tab looks like, and I'm just toggling between those 2 tabs on the top left. So if you don't have much experience with DLS, that's totally fine. It's basically just looking at the movement of the particles in the solution, and it's measuring the fluctuations in their light intensity over time. And it's using that to calculate the sizes of particles in the solution. And I should also say, if you are very familiar with DLS, with this, you have the flexibility to go in and look at the raw data. You can look at the correlation functions, and you can change the default setting. So it gives you that capability too. Okay, so why would I choose to do this? Why would I collect this? So the initial DLS, which is at the beginning before I start ramping up the temperature, that can tell me what state my protein was in before I started the experiment. So if it doesn't look the way I expected it to, if it's showing some aggregation already, that would be useful for me to know. And then the final DLS at the end of the thermal ramp, that can tell me what's happening after it's been heated up and subjected to this thermal stress. I can see what happened to the distribution of particles and their sizes. And of course, I should mention, you don't have to do a heat ramp all the way to 95. So you might choose to do an experiment where you just ramp up to 45 or 60 degrees, and you want to see what's happening to your proteins under that kind of thermal stress. So it can be useful to just sort of check. So here I have the same heat map on my analysis screen. And again, I can choose the parameter that I'm color coding the data by. And then I have a table below with all the analyzed values that Uncle has calculated. And then it's showing me 3 different types of graphs. So the raw data is on the top right in the form of correlation functions. And again, you can ignore that if you want to. And then the intensity and mass distributions show you the calculated sizes of the particles in your solution. And you can also select multiple samples to overlay like I've done here to compare. So here I'm pulling out just the intensity distributions for my 2 antibodies, 2 and 10, at the beginning of the heat ramp and at the end of the heat ramp. So you can see there's a striking difference here. So they both started with the expected size of an antibody, which is sort of between 10 and 11 nanometers here. But then by the end of the thermal ramp, antibody 2 has just increased a little bit to sort of a modest 42 nanometers, and it stayed there, where antibody 10 has shot up all the way to greater than the size that my machine can measure. So it's greater than 1,000 nanometers. And then if you look at this value on the table below called PDI, or polydispersity index, that is a measure of how homogeneous my sample is. So basically how uniform the size of the particles are. And you can see that antibody 2 at the end of the ramp still has a quite low number. That's under 0.4, which is considered fairly uniform. Whereas at the end of the ramp, antibody 10 has this really high value of over 2. That implies there's just a whole mixture of different sizes of particles, ranging from very large ones. And so this data is telling me the exact same story as the SLS light scattering did, but it's just giving me more confidence in what's going on. So it's telling again that antibody 2 is not forming any large particles, and it's staying a little bit more homogeneous. So if I summarize all the data that I got from this one single experiment that used very little sample, the TMs for the 2 antibodies, again, they were very similar, 67 to 68. And the T-ag was actually higher for antibody 10. So if I stopped right there, I might conclude that it was the more stable one of the 2. But if I then look at the next set of data, which was the intensity values of aggregation by SLS, then I can see that antibody 10 is actually more prone to aggregating, in these larger particles. And when I look by DLS, the bottom part of the graph or the table, again, I see that it's forming these much larger aggregates that could prove to be problematic later on in my processes. So I can combine this with the data I've gotten from different types of assays, different types of instruments, and then when I think about what I'm trying to develop, and it just can help me make a decision with more information. So here's a summary of what I just said about that case study. So again, antibody 2 was less prone to forming large aggregates in PBS. And now I just wanted to show a really short case study of how you can follow basically the exact same steps, but to carry out a formulation screen. So all of my antibodies before were in PBS, and I want to know whether I might be able to improve my candidate a little bit by adjusting the salt or the pH of the buffer. So just for the purposes of illustration here, I've kept it simple, and I've just gone to the extreme ends of pH from 5.5 in pink to 8 in blue. And then I went to extreme salt conditions from 0 salt to 500 millimolar NaCl. And so just to sort of, hit those ends and see what happens. So as you can see, those 4 different conditions on the top graph, they actually had no significant effect on the TM. So all 4 TMs are fairly close. So it looks like it's not, drastically changing the unfolding of the protein. But if you look at the aggregation graphs on the bottom, that tells a pretty different story. So the the 2 pH 8 curves in blue, they seem much more optimal for this antibody. So they're staying really low on the y-axis. They're not showing much aggregation. At pH 5.5, you're getting a lot of aggregation to the point where it's actually appearing to precipitate out of solution at about 75 degrees. And adding a lot of salt doesn't seem to help at that pH. So I can kind of conclude just from this tiny set of formulations, I can conclude that pH 8 seems more optimal, and low salt actually seems better for pH 8 as well. So now I can sleep well at night knowing that the PBS I was using before was actually a pretty good choice of formulation. And if I go lower in pH, that's not likely to improve my formulation. So of course you could do this with a much broader set of conditions and do it really quickly, but I just wanted to show just a little slice of that. Okay, so now I just wanted to take a couple minutes to mention that with these different detection modes, the fluorescence, the SLS, and the DLS, there's a lot of different ways you can use this instrument. So the experiment we walked through actually used all 3 at the same time. But you can do applications with just one mode or a combination of 2 of the modes. And there's a lot of different ways that can give you useful data as well. So for example, you can choose to use this just as a DLS reader. So you don't have to do any thermal ramp at all. You can just run anywhere from 1 to 48 samples at a time. And you can get DLS data with the automated analysis that we do. So here, just as an example, I ran 5 antibodies out of the fridge, and I just collected DLS data. And 4 of them looked exactly as I would expect, with a size of about 10 nanometers. But one of them was showing aggregation after storage. So I can kind of, as just a QC check, I know that I need to do something to fix that one before I move on. So maybe it got freeze-thawed too many times or something like that. So I know there's a problem before I start working on it anymore. So this is just a useful way to use the instrument, as well. So another way that you can use the instrument using a combination of 2 modes are to collect these parameters called B22 and KD. So you might also see different names for these like A22 or B2. And these are pretty commonly used ways to measure aggregation propensity, which basically means how likely is your molecule to interact with itself as you move to higher concentrations. And so as Joe mentioned earlier, as biotherapeutics move towards higher and higher concentrations, this is becoming really important because you start to worry about things aggregating in the vial. So for both of these parameters, you basically measure a protein at a range of concentrations. So on the x-axis there, you've got increasing protein concentration. And on the y-axis, you're plotting a line against some sort of measurable value. So if that line is horizontal in the middle of the triangles, then you can kind of conclude there's no major interactions, and that's sort of ideal or expected behavior. If that line slopes positive, then that tells you that there's repulsive interactions between your molecules. So that means the protein would rather interact with a solvent around it than with itself, which is actually usually pretty good if you want to formulate something at a high concentration. And if the line slopes negative, that means the proteins would rather interact with each other than with their solvent, and that's probably meaning that you're going to face aggregation down the road. So this is very formulation dependent, and so you can quickly test your protein in different conditions and find a condition that will minimize the risk of aggregation. So this is really about sort of reducing your risk. And so UNCLE measures these two parameters independently by two different measurements, but it does it at the same time. So you get both of them out of the same set of samples. So for B22 on the left, the measurable value that you're plotting on that y-axis is related to the scattering intensity of the sample. And for KD on the right, the measurable value relates to the size of DLS, the DLS measurement of the sample. So I guess if you think intuitively about the size of the molecule, if you increase protein concentration, if there's no interactions happening, then you really wouldn't expect the size to change as you go higher in concentration. But if the molecules are attracted to each other, you can imagine that as you increase the concentration, they get closer to each other in the solution. The measured size might be different than expected. So that's where that comes in. So for measuring B22, as I said, that relates to the scattering intensity of the sample at different concentrations. UNCLE uses this equation here. And to run an experiment, you don't need to do any math at all. The analysis is totally automatic, just as it was for the other applications. But if you are interested, the standard method of doing this is to take to measure the scatter of something known. In this case, we use toluene. And so it takes the measured value from UNCLE of toluene, and it puts it into this equation with these known values that are indicated in green. So it takes those and plugs them into the equation to calculate the R theta value, which it uses to plot the line for the B22. So the actual experimental setup to do this application is very simple and quick. So you just take a protein. We recommend a maximum concentration of about 20 or 25 mg per mil. And then you make a few dilutions going down. So we recommend using about 4 or 5 different concentrations just so that you get a good line fit. So this way, if you kind of do it the way that I've laid out here, you can get one condition in each uni. So you could run 3 at a time. And then you can still have a blank for your buffer alone to sort of normalize your scattering from the buffer. So you would just load those into the uni, put them into the UNCLE, hit start, and then walk away. And it only just takes a couple minutes. So you just go check your email, and then you come back, and the data is analyzed. And it looks like this graph right here. So for this example, I'm just going to be walking through lysozyme, which is a small protein, a good model system. And so here it's in a buffer with either 100 millimolar salt or 400 millimolar salt, NaCl. And if you store lysozyme in a high salt buffer in the fridge overnight, you can actually see the aggregation with your eyes. It just turns really cloudy. And that's reversible. So if you dialyze it into lower salt, the cloudiness goes away. So we know that it's not like denaturing or precipitating. So this makes a really nice model system for showing how these two parameters work. And you can see the radio button on the top left. So I can just toggle between my KD result and my B22 result on this same screen. And then you can also see below the graph, there's this little toluene intensity box. So that's where I can enter my toluene value that I measured separately. And I can do that either before I start the experiment, or I can change it later and it'll recalculate the data based on that. So this is the B22 result, and then if I just toggle to the KD, this is what the data looks like. So in both cases, the blue line is the low salt buffer, and that shows a positive slope, which indicates repulsive interactions between the protein molecules. And then the gray line is the 400 millimolar NaCl buffer, and that shows a negative slope. So that indicates that the molecules are attracted to each other and they have a propensity to aggregate, which is indeed what you see if you leave it overnight. So the values that we get, they're reported in the table below, and those match really closely with what has been reported in the literature with other methods. So people do this in many different ways, and so there's a lot. Lysozyme is a very common model system, so you can look and find examples to use here. Okay, so to summarize, I think what we've shown you today, just a few of the things that you can do with UNCLE. So in many cases, you can do them at the same time using the multiple detection modes simultaneously. So the TM, TAG, and sizing, polydispersity, or the B22 and KD at the same time. So the advantage to using just one instrument to get all of this data out is it saves you lab space, it saves you time, so you don't have to be trained on multiple instruments. or remember how to use different software packages. And of course, you don't have to burn through as much protein for every experiment. And then finally, this is what we call the zero-click analysis of the software. That means your data is analyzed automatically. That just really saves you time so that you're not running into bottlenecks with data analysis. And you can imagine there's a lot of data that you can collect in a short time, so 48 samples at once with 3 different detection modes. That could give you lots of data in just a couple of hours, and you don't want to have to spend a lot of time analyzing that. So this makes it that much easier. Okay, so thank you so much for listening to us today, and I'm going to hand it back to Anna, and we can take some questions now.
Okay, thanks very much, Joe and Dina. I'm sure you'll all agree that there were some excellent points raised during the presentation. We have had a number of questions, so we'll move straight on to those. I'd just like to remind you that you can still continue to submit your questions during the Q&A session. So, Dina, the first question we've got for you is, what are the upper and lower limits for protein concentration for measuring B22 or KD?
Yeah, that's a good question. So for B22, it's not a limit of the instrument, but it's sort of a limit of when the fit is linear. So we recommend going the upper limit sort of as high as 20, 25 mg per mil. And so if you're familiar with people who have been doing this with analytical ultracentrifugation, you can go really, really high to like 100 or 200 mg per mil. This is not that type of technique. So this looks more as sort of a correlation, and it sort of predicts that you see this line fit, and if you see a positive slope or a negative slope, then you can kind of like predict that this is going to happen at higher concentration. So we recommend starting at about 20 and 25 and then going down. I wouldn't go down much further than about 1 mg per mil, I think. So that gives you, a lot of room to try a few different dilutions.
Okay, excellent. Thanks, Dina. The next question is there any interference of any excipients present in sample, pH, or other factors on results?
Yeah, that's a good question too. So again, we're looking at intrinsic fluorescence here, right? So if you have a case where you're putting excipients into your formulation that have fluorescence, so if they're sort of tryptophan based or anything like that, then you might see some interference in that case. And often that can just be subtracted in the background because you can run a buffer alone. So that isn't a problem usually. And I can also mention that if you do see that, you can always add a dye, right? So there's other ways around that. But it's rare. I think it's the rare excipient that would interfere with the fluorescence signal. And then by DLS, again, if there's fluorescence, that can make a sample not great for DLS. But you can also see sometimes some sugar molecules like sucrose or trehalose. Sometimes they show up as tiny, small peaks in the DLS, and you can easily filter those out or just ignore them because you know what they are. So I think in general this is pretty amenable to lots of, a big range of excipients. And of course pH too.
Okay, thanks, Dina. The next question we've had in is, how often do you have to measure toluene between B22 measurements?
Okay, so for this, we've done a lot of testing internally, and we find that we recommend, if you're doing this regularly, we kind of recommend just putting toluene in a uni and measuring it about once a month, and that's usually enough to just account for any just natural drift over time. And so, like I said, you can do the measurement after the case and enter the number in after you've done an experiment. Or say you're about to embark on a big set of experiments, you can just do it right before and then use that number for your whole set of experiments. So you really only need to do it periodically if you're running experiments once in a while. And we have, in our manual, we sort of have an easy description. You just fill a couple of wells with toluene and you just read them in the uni. You get that. You just average the scattering intensity and just plug that into the software.
Okay, great. Thanks for that, Dina. The next question is, do adding mineral oil to samples improve thermal ramp studies?
No. So the advantage of using our uni consumable is that they're sealed with little silicone seals. So you don't need to add any oils or anything like that. So you just put your protein in these quartz micro cuvettes, and you seal them, and then there's no need for messing with any kind of messy oils or anything like that. So it's sort of a clean system, free from contamination or anything dripping or leaking.
Okay, brilliant. Thank you. Next question is it possible to characterize more than one TM?
Yes, that's a good question. So it'll find as many TMs as, by looking at the differential curve, it'll often see multiple TMs. And in the antibody set that I showed, it was actually only picking out one TM for all of those in PBS. But often if we use the same set of antibodies and we change formulations, sometimes you'll see another transition appearing. So that tends to be, for the protein, at the protein level, that tends to be formulation dependent. But yeah, it will certainly pick out multiple TMs. It'll report all of those in the table.
Okay, brilliant. Thank you. Next question we've had is, did you try Uncle with virus-like particles?
Yes, we have done some DLS with the virus-like particles on the Uncle, and they tend to be a nice size. So as long as they're pretty homogeneous in size, I would say you can get nice DLS data from particles of that size. And I think in terms of the fluorescence, again, it depends on how many proteins are on the surface, what you are trying to do. But yeah, we definitely have some customers that work with VLPs or other types of things like that, and they get good workable data from that.
Okay, thanks. And the next question is, all this measurement is done at very low concentration. As you know, AB will behave differently at higher concentrations. So what is the highest concentration you can go to all the measurements that you did?
Yeah, so that's a good question too. And the answer is different for fluorescence versus DLS. So by DLS, you can actually go quite high in concentration. You will see a change in the measured size at those high concentrations. And that's just physics, basically. As you get really high in concentration, then the particles move differently because they're so close to each other. So you can still measure sizes, but they might be slightly different. So you can go, 100 mg per mil, you'll still be able to get good data out. And for fluorescence, again, the aggregation that you see is going to be slightly concentration dependent too. So if you go to very low concentrations, you might see less aggregation just because the particles are less close to each other. But we recommend, anything to about 150 mg per mil should be fine for fluorescence too. So basically, it's a wide range. I would say you can go pretty high. Again, with the B22KD, that's a little bit different because the technique for that has limitations where the fit starts to get not so linear at very high concentrations. So that's kind of an exception. But for all of the TM, TAG, DLS measurements, you can go 150 or plus mg per mil. And again, that's protein dependent, right? So we're mostly talking about large proteins here. So for small proteins, it just depends on the molecular weight of the protein.
Okay, thanks, Dina. The next question we've had is, why don't you measure DLS at the same time as the thermal ramp?
That's a good question. It comes up a lot. So if you think about how long DLS measurements take to do, so we usually collect about 20 seconds of DLS data, whereas the fluorescence and SLS takes less than 2 seconds per well. So when we're scanning to do a thermal ramp, we're scanning really quickly and collecting the full spectra really quickly, and so you're getting good data resolution in that ramp. And so if we had to pause for 20 seconds at each well to take that data, then you would be missing out on some transitions. So what we offer, we do offer an application that's on that list that's called DLS thermal ramp. So what you can do is you can just collect DLS at every point on your thermal ramp. And you can do that instead of collecting fluorescence and SLS. But we don't want to sacrifice, with our standard TM-TAG, we don't want to sacrifice that data, density by stopping at each well for a long period of time. So you can choose, you can do DLS or you can do fluorescence and SLS, depending on what you're trying to look at. And again, you can pause at some point and take DLS. You can set up an experiment where you ramp up partway, pause, collect DLS, and then ramp up more. But we just don't want you to miss those transitions by waiting for too long.
Okay, thanks for that, Dina. We've had another question through that says, Do I have to run 48 samples at a time, or can I run partial or only one uni?
Oh yeah, you can actually just run one sample at a time if you want. So you can fill one well of the uni, or you can fill all 48. And so I think I showed when you're loading the samples in, you can see them turn green when they're full. So it just kind of gives you a visual representation of how many of the wells you're using. So you can, the machine doesn't care if you're using 1 or 48.
Okay, perfect. Thanks, Dina. The next question is, if I have around 1% of protein A and around 99% of protein B, can I precisely quantify them? And how different their size should be in order to avoid overlapping?
So I assume you're talking about DLS size measurements here. So with DLS, there's a limitation where proteins have to be at least 3 times different in size to be able to resolve the difference. So if you have a mixture of, say, monomer and dimer or monomer and trimer, you can't resolve that by DLS. That's not the right technique. You would want to use a different kind of technique to resolve that. Or you would want to separate those on a column and then run them on DLS. But if your proteins are large enough, there's a large enough difference in size, then you can absolutely get 2 separate peaks. Resolving the 2. So it really just depends on the sizes of those 2 proteins.
Okay, thanks.
So if you have like a monomer and then an aggregate that's like a 15 mer or something, you can definitely resolve those.
Okay, brilliant. Thank you. The next question is, how pure does the sample need to be?
So again, this is going to depend a little bit on how much background, proteins you have, how much background fluorescence you have. So if you can do a background subtraction by running, some sort of blank, then that's often possible to do. But if you have a lot of proteins in your background that are contributing to the fluorescence, then it might be difficult to get a TM out of that. And I think that's pretty standard for any kind of TM measurement, right? If you have a mixture of proteins, they're going to all contribute to that signal. And so in that case, if you can't purify something, you might consider using a dye in the system instead.
Okay, brilliant. Thanks. The next question is it possible to measure protein-protein interactions with UNCLE?
I assume you're talking about something like, I'm trying to think through this. So there are some DLS-based techniques for measuring protein-protein interactions if you hold one constant and increase the other one, and you can kind of look at size changes. We don't currently have a standard application for that. We're interested in it, and so we're sort of thinking about it for the future. But I think, for now, you get all the data out, so you can take the data and do whatever you want with it if you know of a technique that does that well.
Okay, brilliant. The next question, Dina, is for KD measurements of polydispersed samples, is there a way to isolate the diffusion coefficient for a single peak?
Oh, okay. So the software uses, by default, it uses the peak 1 to do the KD measurement. And so you can set a filter that basically, if you know that your protein is not, if the main peak 1 is not where your protein is showing up, then you can change the default filter to ignore whatever you don't want it to look at. So basically, you need to pick a peak because it needs to use that size, right? And so you can, by manipulating the filters, you can tell it which peak to look at.
Okay, thank you very much, Dina. Unfortunately, that's all we've got time for today. I'd just like to remind everybody that any questions we didn't have time to get to today will be answered offline as soon as possible. The webinar will now be available on demand, so if you have any friends or colleagues that you think may be interested in the webinar, please feel free to share the link, and I'd like to thank you all again for your time.